Calculations of conservation of energy. So the first examples that we're going to use are just going to be either potential energy or kinetic energy. So the first question is, what is the total energy of a 30 kilogram object that is at a height of 40 meters? So this is a situation in which I only have potential energy because there is no velocity, nothing's moving. If there's no velocity, there's also no acceleration, so there's no work loss due to friction. So my total energy is equal to my PE, which is mgh, and so that will be 30 times 10 times 40, or 12,000 joules. Here's another example in which all I have is kinetic energy. So the question is, what is the total energy of an object that has a mass of 150 kilograms and a velocity of 10 meters per second with no friction? So there's two clues that there's no friction. One, I tell you there's no friction. The second one is there's no displacement, right? So work loss due to friction has to occur over a certain displacement. If that's not given, then you can assume that there is no work loss due to friction. So because there's no height, no change in height, the potential energy is zero. I already told you that there's no friction. So now all I have is kinetic energy, which is 1/2 mv squared, which is 1/2 times 150 times 10 squared, and that equals 7,500 joules. Now we're going to get into the conservation of energy where things start to change. So I have two situations. I have the ball at the top of the hill, and then it rolls down the hill to the bottom of the hill. So the first thing that we calculate is the total energy at the top of the hill. At the top of the hill, all we have is potential energy. The potential energy of the ball at the top of the hill is going to be 8,000 joules, and that comes from the mass times g times h, or 20 times 10 times 40. At the bottom of the hill, there is no height. It's at the total bottom that it could be, so the height is equal to 0. Anything times 0 is equal to 0. So my change in potential energy has gone from 8,000 joules at the top to 0 joules at the bottom. My total energy at the top is equal to potential energy times kinetic energy times work loss due to friction. Because nothing's moving at the top, all I have is potential energy. So my total energy at the top is equal to 8,000. My total energy doesn't change. That's the conservation of energy. So my total energy at the bottom is also 8,000 joules, and that's going to be equal to potential energy times kinetic energy times work loss due to friction. I have no height, so my potential energy is 0, and I told you that there was no friction, so there is 0 work loss due to friction. So at the bottom, my total energy is just my kinetic energy. So because my total energy at the top is equal to 8,000, which is also my total energy at the bottom, and that's just equal to my kinetic energy at the bottom is going to be 8,000 joules. So it's 8,000 joules at the bottom of the hill, 0 joules at the top of the hill. So it's a seesaw, right? At first, all I have is potential energy, and as the ball goes down the hill, the kinetic energy, it starts to transfer to kinetic energy, and at the bottom of the hill, I have no potential energy. So now we're actually going to figure out what the velocity is, because that's one of the things that we can use with conservation of energy. So we figured out that the potential energy at the top of the hill is going to be 8,000 joules, and at the top of the hill, all I have is potential energy. So my total energy, my TE at the top, is going to be equal to 8,000 joules. And that TE at the top is equal to my TE at the bottom as well. And at the bottom, we figured that is only equal to KE. My KE is equal to 1/2 mv squared. So if I'm solving for velocity, I'm going to say that TE is equal to 1/2 mv squared. I'll multiply both sides by 2, then divide both sides by m, and then take the square root. So I have the square root of 2 times 8,000 divided by 20 is equal to my velocity at the bottom of the hill. And that ends up being 28.2 meters per second. That's pretty fast, but you're also falling basically 4 high dives worth of height, so it makes a lot of sense that by the time you're at the bottom, you'll be going very fast. Well, what happens if I have friction? So here I have the same situation, the 20 kilogram mass at the top of a 40-meter hill, but now I have 120 joules worth of friction force that had to be used, work lost due to friction, that had to be used because there was some friction on this slide or this hill. Again, I start out, total energy at the top is equal to nothing but potential energy because I'm not moving. So it's equal to 8,000 joules. TE at the top is equal to the TE at the bottom is equal to TE everywhere. At the bottom, now that I have friction, I have to say that even though my potential energy is 0, because my height is 0, my TE is now equal to my KE plus my work loss due to friction. So if my work loss due to friction I know, and I'm looking for my velocity, to isolate for V, I'm going to use TE minus W, work loss due to friction, is equal to 1/2 mv squared. I'll multiply both sides by 2, divide both sides by m, take the square root, and it ends up being 28.1 meters per second. So it's not that much slower, but my work loss due to friction wasn't really that much, so it kind of makes sense. Now what happens if I have to go partway down the hill? So if I have to go partway down the hill, then I'm not going to have a 0 height, and so I'm not going to have a total conversion of my potential energy to kinetic energy. So here's a question of what is the velocity of the ball 10 meters from the bottom of the hill? 10 meters from the bottom of the hill, I still have some potential energy and kinetic energy, but I start my calculations the same way. I start at the top of the hill, where all I have is potential energy. I don't have kinetic or energy or work loss due to friction because there's no motion. Now, again, we're not going to have to worry about work loss due to friction at all, so we're just looking at potential energy and kinetic energy. So at the top, all I have is PE, and so I trace that through, same numbers again, so it's going to be 8,000 joules. So that TE at the top is going to be the total energy everywhere, even at 10 meters from the bottom of the hill. So that total energy will be equal to potential energy plus kinetic energy. Now my potential energy I know is mgh, that's no problem. And because my h isn't equal to 0, I have to include that in my calculations. So I'm going to solve for V again. So I subtract mgh from both sides. I multiply both sides by 2, divide both sides by m, take the square root, and that will be my velocity at 10 meters. So I plug this in, remembering, this is my TE, that the height that I'm going to be using is not going to be 0 or 40, it's going to be at 10 meters. So mgh is going to be 20 times 10 times 10. They just happen to be the same number because it's a coincidence. I place that over the mass, and I find that my velocity is 24.5 meters per second. So that's less than 28.2 meters per second, but that makes sense because I'm not at the bottom of the hill. So what we've done in this video is we've looked at total energy, the concept of total energy, and within a given problem, the total energy doesn't change. Sometimes it's just PE, sometimes it's KE. In this case, it's a mix of both. I have potential energy, which would be 20 times 10 times 10, or 2,000 joules. But I also have kinetic energy. If I have a bit of potential energy along with kinetic energy, my kinetic energy won't be at its maximum. My velocity will be less. And similarly, if I have friction at the bottom of the hill, then my kinetic energy will also not be at its highest. I won't have my highest velocity, and that's because, sorry, wrong one, that's because I have work loss due to friction. Not all of my energy was able to be transferred into getting my ball as fast as possible. Some of it had to overcome friction. And we see this in everyday life again. When we have work loss due to friction, then we're not as fast going down a hill. Again, it's faster at the bottom of the water slide, a 40-meter water slide, than if I rolled down a grassy slope, because rolling down the grassy slope, there's a lot more friction there. And so my final energy that is going to be kinetic energy won't be as high. My velocity won't be as high. So the problems that you will have, your total energy will always be the potential energy at the top, and you'll use that to find kinetic energy at the bottom. Sometimes your kinetic energy won't be the maximum because you'll have to subtract work loss due to friction. Sometimes your kinetic energy at the bottom won't be maximum, or it won't be at the bottom because it won't be at the bottom of the hill So I'll still have some potential energy. So sometimes your TE at the bottom will be equal to just KE. If it's at the bottom and there's no friction. Sometimes at the bottom, it will be equal to TE plus KE, will be equal to KE plus work loss due to friction. And sometimes your TE will be partway up the hill, so it will be TE is equal to PE plus KE. So you're never going to have a situation in which it's actually equal to all three at the same time. At least one of your terms will be equal to 0.